Welcome to the session on EST200 Design and Engineering. This subject is included in the semester 3 of all branches of BTech of APJ Abdul Kalam Technological University, Kerala. I am Amita Matthew, Assistant Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. In this session, we will be covering the part 2 of module 4. In the part 1, we have covered project-based learning and problem-based learning in design, modular design, and applications of biomimicry. In this part 2, we will be covering life cycle design approaches, aesthetics and ergonomics in design, value engineering, concurrent engineering, and reverse engineering in design. First topic is life cycle design approaches. A life cycle approach can help us make choices. It implies that everyone in the whole chain of products life cycle from cradle to grave has a responsibility and a role to play, taking into account all the relevant impacts on the economy, environment and the society. Using the life cycle approach, environmental experts, designers and developers are working together to decrease the product's environmental impact. Strategies for disassembly and recycling are considered in the development process itself. Let's look into the details of life cycle design approach. So life cycle approaches to design considers all the phases of product's life cycle during the entire design process from the concept definition to the detailed design development. In this phase, we will be considering the development, production, distribution, use, recovery and disposal. It uses methods and techniques to integrate product evolution from conception to disposal with a wide range of design requirements like performance, cost, and environmental impact. Design should strongly influence product's performance in each phase of its life cycle. Life cycle design approach is generally called as design for X, where X stands for different properties of the product or phase of its life such as manufacturing, assembly, environment, safety, quality, maintenance, etc. Let us see which are the different design for X or what this X stands for. First X is design for manufacturing or construction. Then design for assembly or fitting, DFA, design for quality, DFQ, design for safety and reliability, design for maintenance and serviceability, design for logistics, design for environment, that is disassembly and recycling. First design for X is design for manufacturing or construction. It is also called as DFM. The main objective is to make the cost of realization of the product low and improve the total product quality. It uses standard parts or subcontracted items, and it uses wide tolerances wherever possible. It also uses a method called group technology, and group technology is a manufacturing technique in which parts having similarities in geometry, manufacturing process or functions are manufactured in one location using a small number of machines or processes. So in group technology, parts are grouped based on their similarity in design attributes and manufacturing. Such parts form a family or a group. This reduces the total cost of production. The first part of the figure shows different random parts required for manufacturing the product. And in the second part, we can see the parts are grouped together based on its similarity. DFM guidelines. The heart of any design for manufacturing system is a group of design principles or guidelines that are structured to help the designers reduce the cost and difficulty of manufacturing an item. The following is a list of such rules for DFM. So minimize total number of parts, standardize the components, use common parts across product lines, standardize design features, aim to keep design functional and simple, design parts to be multifunctional, design parts for ease of fabrication, minimize secondary and finishing operations. These are the various guidelines for design for manufacturing. Next is design for assembly. Assembly is often the costlier part in manufacture. Manual assembly is very costly. However, by designing the product suitably, many assembly operations can be automated. And assembly automation reduces the time and cost. Vertical assembly is good for the ease of assembly. Reduction in screws and quick location of parts make the assembly move fast. Design for assembly guidelines. Minimize the total number of parts. Provide self-locating features on parts. Design parts with self-clamping features. Avoid reorientation of parts during assembly. Use top-down approaches for assemblies. Use standard parts in the design. Think of modular design. Next is design for quality. Quality of design is defined as a fit between a product's design and customer needs. Quality is defined as fitness for purpose or as the measure of customer satisfaction. Quality of a part or a product or a component refers to the product features that meets customers' needs and satisfaction and avoidance from deficiencies that would minimize the chance of failure of the part. By embedding quality control checks throughout manufacturing process, quality by design allows you to optimize your production, improve your product and streamline your process. Embedding real-time quality control checks is just one of the control strategies that help ensure product quality. David Carvin in 1987 defined quality in 8 basic dimensions for a manufactured part. Let's see what these 8 dimensions mean. First is performance. Does the product perform to its standards? Does the product provide the intended service? Features. What additional benefits may be added to the product? Will there be any tangible or intangible benefit? Reliability. Is the product consistent? Will it perform well over its lifetime and perform consistently? Durability. How durable is the product? Will it last with daily use? Conformance. Does your product meet with any agreed internal and national specifications? Serviceability. Is the product easy to service? Aesthetics. Is the product appealing to the eye? Perceived quality. What sort of quality perception does the marketing team want to convey in the marketing message? Will the price charge reflect the quality of the product? These are the 8 dimensions defined by David Garvin. Importance of design for quality. Design is more responsible for quality than anything else. The designers largely influence the entire procurement, manufacturing and assembly cycles of any small part or large component. Both design and manufacturing are responsible for the final quality inherited by a part or a component. If the quality is envisaged appropriately in the design procedure itself, the quality in manufacturing can also be ensured at lesser expenses and the cost of inspection reduces significantly. This leads to the concept of design for quality. Design for safety and reliability. Safety is achieved through the use of reliable structures, components, systems, and procedures. Reliability is the probability that a system or component will perform its intended function for a prescribed time and under stipulated environmental conditions. Safety is to be ensured during the design phase itself, and this covers the materials used, design aspects on safety in operation, foolproofing, warning systems, etc. What are the safety systems which are needed in an automobile? Airbags, seat belts, lane departure warning systems, adaptive cruise control, driver monitoring systems, blind spot detection, night vision systems, etc. are some of the safety features available in automobiles. Reliability is the probability that a product will perform its function under normal use for a specific period. And design for reliability ensures that products and systems perform a specified function within a given environment for an expected life cycle. Normally, for simple understanding, reliability can be specified as mean time between failures. Reliability is associated with unexpected failures of products or services. In order to improve the reliability, redundant systems are used in specific designs. Understanding why these failures occur is key to improve the reliability. Thereby, we can improve the later versions of the system. Design for maintenance and serviceability. Design for maintainability is a process where designers design products with ease of maintenance in mind. Design for serviceability is a process where designers design products to increase the serviceability. Serviceability means the quality of being able to provide good service. Product maintenance is an important aspect to be taken during the design phase. Product should be simple and easy to maintain. Part replacement requirements, spare part needs, spare part availability, etc. needs to be considered. Easy access for part replacement, part interchangeability between models, etc. should be taken into account. Easy access to watch battery is a maintainability consideration. Design for logistics. Design for logistics is a design approach that helps to control logistics costs and increase customer service level. It includes design for packaging, handling, transportation, and storage. Design for seamless transportation should be taken into account. Optimal packaging to save space and damage. Provision for product handling with design for disassembly and recycling. It's also called as design for environment as it tries to minimize or eliminate environmental impact of a product over its life cycle. Design for disassembly is the process of designing the products so that they can be easily, cost effectively and rapidly taken apart at the end of the product's life so that the components can be reused or recycled. Here, the following aspects are to be considered. Design for easy disassembly, no welded joints, no dissimilar materials should be joined together, use common materials as far as possible, easy segregation of parts of the same material, automated disassembly, easy cleaning and compaction requirements, handling of dangerous materials, etc. should be considered. Using same type of screws in the entire product, reduce the number of screws as much as possible, provide indications for detaching, lifting, etc. wherever possible, etc. are some examples of disassembly considerations. Next topic is aesthetics. Aesthetic is a core design principle that defines a design's pleasing qualities. As humans, we are programmed to be attracted to what we find beautiful. Something shiny and something pretty will always catch our eyes and sustain our interest. It's just our way we are drawn to things that satisfy our senses. Aesthetic is defined as a measure of how attractive a product appears. Aesthetic includes factors such as balance, color, movement, pattern, scale, shape, and visual weight. Designers use aesthetic to complement their design's usability and so enhance the functionality with the attractive layouts. Adding appealing aesthetic to design or creating a design with aesthetics in mind means creating in ways that please as many senses as possible. These are some examples of aesthetically designed chairs. Next topic is ergonomics. Ergonomics is how well a product feels when used or held. Ergonomics deals with characteristics, abilities, and needs of humans, and in particular the interfaces between human and technical products. That is, it is the man machine relationship and the application of anatomical, psychological, and physiological principles to solve the problem arising from man machine relationship. The different aspects of ergonomics include safety, comfort, ease of use, productivity, or performance. This is an example of ergonomics design. We can see the eyes are directly pointing towards the source device. The hands can be directly put onto the input device. The body is straight on the chair and the feet are touching on the floor. Many products are not safety critical and the designers must take the responsibility for balancing aesthetics and ergonomics appropriately. Next topic is value engineering. Value engineering is a systematic method to improve the value of goods or products and services by using an examination of function. Value is a measure of how worth a product is for that cost. That is, value is the ratio of function to cost. That is, worth to cost. Value can therefore be increased by either improving the function or reducing the cost. It's a primary tenet of value engineering that basic functions be preserved and not be reduced because of pursuing value improvements. Value is the lowest price you must pay to provide a reliable function or a service. The different steps involved in value engineering are value discovery, value realization, and value optimization. Following are some of the questions to be addressed while implementing value engineering. What the product is supposed to do? What else can it do? What else is needed to enhance the value? Will these secondary functions add value to your product? What are the value added features you can notice in a stapler? Can you think of any additional features that can add value to it? This is a normal stapler which can be used to staple pins to paper. In the second one, they have added the functionality for removing the staplers also. Even though it's a simple change in design, it adds more value to the product. Similarly, we can think about adding more functionalities to stapler like having a paper punching option, facility to insert pins of different sizes, etc. We'll see some more examples of value engineering. Here you can see an adjustable spanner which allows fastening of different sized heads, whereas in the conventional spanners we need to use different size spanners for each of the heads. Many of us are having the habit of having some biscuits along with tea or coffee. But we need to use an extra saucer for keeping the biscuits. But what if we have a pocket for the cup to hold the biscuits like this? It will be so nice. Similarly, these are some other examples of adding value to products. Now let's have an activity. Can you think about adding value to the following products such as a normal laser printer, a ladder, a jacket for winter? Think about adding value to these products. Our next topic is concurrent engineering. Concurrent engineering is also known as simultaneous engineering, and it's a method of designing and developing products in which different stages run simultaneously rather than consecutively. It decreases the product development time and also time to market, leading to improved productivity and reduced cost. What's the need for concurrent engineering? It provides competitive advantage. That is, reduction in time to market means that business gain an edge over their competitors. Then second advantage is enhanced productivity. That is, earlier discoveries of design problems means potential issues can be corrected soon rather than at a later stage in the development process. Next is decrease design and development time. That is, It makes the products which match their customer needs in less time and at a reduced cost. Next is reverse engineering. Reverse engineering is also called as back engineering. It's the process of extracting knowledge or design information from anything man-made and reproducing it or reproducing anything based on the extracted information. The process often involves disassembling something like a mechanical device, electronic component, even a computer program, or biological, chemical, or organic matters, and analyzing its components and workings in detail. How can we perform reverse engineering? It can be done either manually or it can be computer assisted. One can digitize any product and create its CAD model. This model can now be easily modified to create new designs of the same product. An existing product can be redesigned through reverse engineering. And this reverse engineering is good for making spare parts that are not available. Also, it can be used for modifying an existing design.